during the beginning of the talk.
Okay. So can I just start now?
Okay, let me do the formal 30 seconds introduction. So we start again this morning's session with Tai-Ping Liu from Academia Sinica Taipei and Stanford University, who will talk about singular layers for Boltzmann equation. Please, Tai-Ping.
Okay. Yes, thank you. Okay, so let me see. Okay, so I think everybody knows the Boltzmann equation, and I will consider these singular layers, which need a lot of nonlinear quantitative description. And the purpose is to relate the Boltzmann equation to fluid dynamic and the interface where Boltzmann equation cannot be well approximated by the fluid dynamic equation are the singular layer. So this need a strong quantitative analysis, and so we make life easier by assuming the Haas-Freer model. Okay, so here's down here. Now let me at least say a few words about the Boltzmann equation. This is the transport part, and it says that how is the amount of gas changes as one follow the particle trajectory. It changes because of collision. And then there's a K here, which is the mean free path. Okay, so to relate to fluid dynamic, one look at the macroscopic variable here. And so density is the integration of the F with respect to all microscopic velocity c. So this says that it's amount of the gas in the near a point X for with any velocity. So all the gas near there, and then you have momentum, internal energy, stress tensor, heat flow. Now okay, so those are macroscopic variables, and they are functional x and t because you integrate out the microscopic velocity c. Now the collision operator has a property down here. It says that if you integrate the Q times 1, which means that the amount of gas produced locally due to collision, and there's no production. Okay, the collision redistribute the gas in its microscopic velocity distribution, but it does not produce macroscopically the amount, the density and momentum and energy. So the collision operator redistributes things, but it macroscopically does not produce mass, momentum, and energy. And that's because this interaction law at the top here, which says that the velocity before collision and velocity after collision conserve mass, momentum, and energy. All right, so this gives us the conservation laws. You just integrate the Boltzmann equation times 1, and then you get a conservation of mass. Times c, you get a conservation of momentum, and then there's energy. But this is the equation in 3 space dimension. There are 5 equations. However, there are 13 unknowns. So besides the density, momentum, and the energy, there's also this stress tensor, which is a 6 variable, and this is this a heat flow, which is a 3 variable. And so this equation, conservation laws, is not very useful because it's an underdetermined system. The 5 equations, but of course with certain unknowns. Now one can go on to find the equation for P, for example, or equation for V. But then this will involve a higher moment. And you can go on. So one can say that the Boltzmann equation is essentially a system of infinite number of partial differential equations. Now, an important thing is in the study of Boltzmann equation is to find out when Boltzmann equation can be accurately approximated by some finite number of fluid dynamic equation. And so this is made possible by the H theorem. So if I multiply the Boltzmann equation by log f, then instead of get the conservation law, one get the an inequality, something is less than equal to 0. So this inequality is equality if and only if the distribution function is Gaussian in the microscopic variable Kc. So that's the Maxwellian. And the Maxwellian depends on the density, velocity, and the temperature. For the Boltzmann equation is corresponding to the monatomic gas. And so the pressure, velocity, and pressure, temperature, and density follow ideal gas law. Okay, so there are, this Maxwellian is a very special distribution. It depends on 5 variables: density, 3 velocity, and the temperature. Oh, I guess, all right. So maybe I go to next picture. So what the H theorem says is that if you are away from this equilibrium manifold, this is a manifold 5-dimensional, consists of all the Maxwellian. And it's a 5-dimensional manifold. And the H theorem says that you are far away from that manifold, then you tend to approach the manifold. And on the manifold, the collision operator is 0. Now, H theorem tells us that the real action eventually is around the equilibrium manifold. And this, in fact, is a place where fluid dynamics phenomena occur. So let's go backward here. If all the distribution functions really on that manifold, which is hardly happen, but suppose we assume that, then the conservation laws will become the Euler equation in gas dynamics. And this is a determined system, it's self-contained system. Okay, so this tells us that indeed near equilibrium manifold, it should be fluid dynamical phenomena. And on the equilibrium manifold, one can define the classical entropy, so thermodynamic applies. Now, the singular layer is the place where it connects a state far away from the equilibrium to the equilibrium. And I just use this blue color to indicate the one down here is more like a sharp layer, for example. Okay, so to study the singular layer, as I mentioned, it required a strong quantitative analysis. And so one started with the linear Boltzmann equation and try to get something definite quantitatively there. And okay, so I have now here some notion to point out. One is that the linearization is up here. Oh, sorry. Here, okay. This is standard linearization started by Hilbert. And the linear Boltzmann equation has this collision operator. And this is square root m, just a good choice, so that it's usually inner product in L2 eventually one deal with. Now, the linear collision operator is inherited from the collision operator. So what make L0 is the tangent plane to the equilibrium manifold at the point M of linearization. And for a given state G, we will decompose it into two components. One component is on this tangent space. It is a projection into the kernel of L. And then G1 is orthogonal to that. And G1 we call the micro part, and G0 we call the macro part. With H theorem, we understand why we would do that. Now, the Boltzmann, the Euler equation, linear Euler equation would be the projection of the linear Boltzmann equation on this plane, the kernel of L. And so this is what said here. You make a macro projection P0, which is project to that tangent space. And then you project also the flux introduced by this convection term. So this is linear Euler equation. And Euler projects characteristic. This is lambda 1, which is velocity minus sound speed. C is sound speed. And lambda 2 is velocity. So this is usual Euler equation stuff. And this EJ is a form also normal basis. And they are the shape of the wave taken by the linear Euler wave. So down here, I just simply say that P0, which is projection to the kernel of L, now can be written as such. And the P0 is the macro part of G. And you can decompose this. Oh, I miss a EJ here, sorry. This is EJ. Okay, so this are the linear Euler equation. Now, the collision operator, as is known to most people here, for the Haas field model, Hilbert has explicitly computed give explicit form of the collision operator. And the K1, K2 are compact operator, and nu for the Haas field model is behave like a 1 plus Kc, absolute Kc. Okay. So this very explicit form would be used to construct the green function. So what is the green function? Green function is of course, everybody knows what is green function, but I try to visualize it. So you have a background of M because you linearize around the Maxwellian M, and you take initial data, have a bunch of particles concentrated at the x equals 0. I'm doing one-dimensional case, okay? One can do three-dimensional also, but let's focus on one dimension. So all the particles put at x equals 0, and with the velocity c star, so you push the particle, and there's the ocean of Maxwellian in the background. Then what happened? There are two main parts. One is the fluid part, and this fluid part really is quite simple. It's just a heat kernel, but with velocity lambda j, which is the Euler speed, and there's a aj there, which is a dissipation, and this is from Navier-Stokes equation. One carry out the Chapman scope, and you get that aj. And then this wave will propagate in the Euler with Euler shape ej. Okay, so that's a fluid part. Another part, which is I call the particle part. This part says that the initial data, which is a bunch of particles at the concentrate at x equals 0 with speed c star. Now this bunch of particles will continue with its identity, but propagate along the particle path with velocity c star, because that's their velocity. But the decay exponentially minus nu over k, and nu is the thing that in the collision operator found by Hilbert. Of course, this is very nice explicit, but one do not get explicit expression of the green function, and that would be impossible. So what remainder is smoother than particle-like, and this decay in time faster than fluid part. So I have to make a very vague comment here. The fluid part is useful for the study of the Boltzmann solution away from boundary and from initial time. And the particle like wave, they decay exponentially, so they very soon become insignificant. However, on the initial layer and the boundary layer, they are dominant factor. Okay. And the remainder is smoother than the fluid, than particle one, and decay faster than the fluid one. So Sixian Yu and I had this in 2004. Okay, so now we talk about the topic today, which is the singular layer. And this, I think, was mentioned by Harold Grant, and he pointed out there are three type layers: boundary, shock, and initial layer. Okay, so let me skip this one, and let's look at the simplest singular layer, that is Knudsen boundary layer. So let's take the boundary to be one-dimensional, and what are the two-dimensional? Okay, the flow to be one-dimensional, and the boundary is fixed at the x equals 0, and gas region is x positive. Then the Knudsen layer will be a stationary one-dimensional solution of the Boltzmann equation. And this is a hyperbolic equation, at least for the Haas field case, and with the characteristic velocity C1. So on the boundary, you should pose boundary condition for the characteristic which go into the gas, and that's for Cauchy-1 positive. And one would like to, this conclusion layer serve a purpose, is only near the boundary that is significant. So it should go quickly to a Maxwellian m minus m infinity. So this is the typical picture of this conclusion layer. You go very quickly with exponential rate, go to m infinity, and the width should be this mean free path. And many people has make important contribution. I just mentioned this paper by Coron, Gauss, and Sulam in '88. Okay, so so this is a conclusion layer. Now, how do one study the conclusion layer? So here's the equation up there, and let's assume that let's linearize the problem around this Maxwellian at infinity. So instead, so the G, which is a perturbation, will go to 0. Original f of the nonlinear one go to m infinity, linear one go to 0. So if we linearize around m infinity. So I want to analyze the solution of this problem here, just a little bit. First, it's easy to see that the flux is conserved. Okay, and this is because EJ is in the kernel of L. You just multiply the first equation, inner product this with EJ, and the right-hand side will be 0. Okay, and so therefore this you have this flux conservation. Now we will decompose G into G0 and G1. And after some simple calculation from this conservation law there, you find that the macro part of G can be expressed in terms of micro part. Okay, and the micro part is good by H theorem, and for the linear problem and for Haas field model, you have this dissipative, this damping property, and then one have energy estimate. Okay, I know I'm a little bit too brief. However, one noticed that this thinking I just outlined is weak if lambda j is very small. So in short, the analysis give us an exponential decay, but this exponent alpha will be very small if one of lambda j is close to 0. And precise because this representation of macro internal micro is very weak if one of lambda j is near 0. So this is a serious problem because what we are doing here is linear analysis. And we can turn linear into nonlinear analysis. And that will be something like a dynamic system typical thing. Since we have a spectral gap, this alpha is a positive number. But alpha has become very small, then the spectral gap will vanishes as one of the lambda j go to 0. So I have this impressionistic picture here. If lambda near lambda 1, lambda 2, or lambda 3, 0, the nonlinear wave here has a good neighborhood. But as one go to closer to say lambda 1 equals 0, then the nonlinear, you go from linear to nonlinear series, this becomes weaker and weaker, and the neighborhood becomes to shrink. So what happened if we want to have a good nonlinear theory, and we do not shrink the neighborhood? What happened? Well, then the collision layer does not exist. Instead, it's a collision fluid layer in its place. Okay, so here is the picture. So if we are near one, say in this case, near lambda3 is 0, then the boundary layer will have one part which is like collision type, and then they will have followed by either expansion wave or compression wave for different value of m infinity. So how do one study this kind of combination? Let me show you another picture first. So what happened is that you start from a boundary function, and then you go to collision type layer, and eventually, and this is exponential decay with a good exponent away from 0. But then the fluid effect kick in, and you have either compression wave or expansion wave. And included in this picture is a shock profile in the middle here. And there are exceptional cases. For some very special initial data, actually it has a collision layer, no fluid participation. And that we call it the Sonnet neighborhood manifold in honor of the Kyoto school, Yoshio Sonnet. And they also come up with this picture. Okay, so let me go back to this one. So how do we construct such a flow pattern? The first thing strategically is that we don't solve a particular boundary value problem. Instead, we consider the totality of all the stationary Boltzmann flow, and they follow the dynamic system, the center manifold, stable manifold, unstable manifold, and so on. And we will use the green function because this provides a strong quantitative analysis. So if I have a solution F, and with F with a boundary data B, given for OC, which never happened because you don't know the boundary. You only know half of it if you consider physical situation. But nevertheless, assuming we know the boundary B, then we get a green identity. This is a green identity. And then we do time asymptotic analysis so that this T go to infinity. So then we focus on this boundary integral operator. This is held by the explicit understanding of G. In any case, I will skip that because this is a very serious effort by Shixian and I, because it's based on green function, and this is okay. In any case, I apologize that I know some people are interested in knowing this stuff, but it's not easy reading. I'm thinking of rewriting the thing and include the other singular layer and put a paper in the bulletin in the House Journal of Academia Sinica. Okay, so I say it's very vaguely here. First, one use the green function, as I already mentioned. And then we have a center manifold reduction, which allow one to use the fluid nonlinearity to control this compression wave, expansion wave, and so on. Okay, so this is much I want to say about the method. Now there's an interesting bifurcation here. You see that if you are on the right, you get the compression wave, you get the expansion wave. And if you are on this part, where you either go to the right or you go to nowhere, and there's no stationary flow there. So this bifurcation manifold. So this picture indicates that there are very striking bifurcation phenomena. And this has been obtained by the Kyoto School over the 80s and the 90s through extensive numerical computation and asymptotic analysis. And we offer some analytical understanding. Okay, so let me talk about the different subjects. So far, we talk about the boundary layer. Now I want to talk about the coupling of initial layer and shock layer. So there's a paper by Shijian in 2014 on this problem. So let's start with the Riemann problem. Now, Riemann problem is important for hyperbolic conservation, though. And it is also important for Boltzmann equation because for one thing, you can scale x and t. So for x large, k becomes small and so on. And so it's related to zero mean free path problem. Okay, so here's an order equation. I'm going to take a particular case where this initial data defining the Maxwellians corresponding to a single order shock. But then we walk through the Boltzmann equation. And then it turns out that the picture is much more complicated because for the Boltzmann equation, this initial layer. For the order equation, it's only a shock wave. But for the Boltzmann equation, there's initial layer. And so this is a coupling of shock and initial layer. And it creates many time scale. The first one is a kinetic layer. And that is basically a hyperbolic. And this is a parabolic thing. And then nonlinear wave began to form. And eventually, time asymptotically, it go to a Boltzmann shock wave. So let me describe this a little bit. Or I should also say that this is very small layer because if mean free path is small, it's very small. And this become large if the wave is weak and take time to form. And the nonlinear to nonlinear wave formation is of this form. It's an even bigger time level with the additional log ipsium. Okay, so now let's talk about initial layer one, which is this one here. So first, the initial layer for the weak shock, we can linearize, which will be accurate. And so the initial data, if I linearize around the n minus, then it will be 0 on the left, and the right will be just a linearization of n plus minus n minus here, which I call it G plus here. Okay. Now, because it's a very short time, so the dissipation and so forth has not really come into play. So it is a hyperbolic scale, and it is dominated by the particle-like wave propagator in the Green function, and which is this one, which I call the particle-like wave in the Green function. So you use this operator to act on this initial data there, and that's what you get. Okay. For the solution, the left, because I linear around n minus, so the left and the right is a perturbation of n minus. And you do computation, you see that this is true for C1 greater than x over t. And for C1 less than x, x over t, then you've got this propagation of this left state here. Okay. Here's the diagram. So initial data on the linear level is 0 here, and this is G plus there. So you draw the characteristic curve because this is what the particle light wave tell us. So you got only information for C1 less than x over t. Now this give sorry. Okay, so this is how this thing down here is obtained. If one look at the macroscopic variable, so one integrate with respect to C, then you see that it is a function of x over t. So this is why it's a hyperbolic scale x over t. Of course, all these approximation, but they are accurate. Now let's look at initial layer, the second one. So we look at this one now. Viscous fluid layer. So viscous fluid layer now is the parabolic scale x squared over t. And this is because there's a fluid part in the green function. And so it's a wave gradually to expand parabolically. Now, if we want to, since we will eventually want to start the nonlinear wave, say if we have a Boltzmann shock, then its width is k epsilon minus 1. If it's a weak wave, epsilon small, then the shock wave will become very wide. And so it takes, if you want the x to be of this width, then the time it takes will be k to the epsilon minus 2. And that's why this width of this viscous fluid layer has this very long time to achieve. Okay, so this is now the third one is the formation of nonlinear fluid wave. I'm sorry to bore you with this, but I will just try to tell you that this is a rich wave phenomenon to go from this initial layer gradually linked to the shock layer. So this one is the one where the Boltzmann shock began to form, and it takes this extra log epsilon time to form. And this is coming from the Hofkohl transformation of the Berger's equation. First, one approximate the Boltzmann equation by Navier-Stokes in this case, and then approximate the Navier-Stokes by Berger's equation. That was my earlier work in the 1980s. And David Hoff and I look at Navier-Stokes shock formation, and I realized that one need to use this Hofkohl transformation. So this is, in some sense, we are just try to use whatever there is available. Okay, anyway, after this one, then one began to say that the solution will go to the real Boltzmann shock. And that there's a paper by Yu, oh, sorry. In 2013. Okay, so this is analysis for time asymptotic state. All right. Okay, so this is the coupling of the shock layer and initial layer, and it takes so many different scales. Now I want to turn to a couple more examples, and this is the Rayleigh's problem. So the Rayleigh problem, let me show this by this picture. So you have a boundary here, you have a boundary here, and this boundary here, the solid boundary, but you move the solid boundary tangentially from the gas region. The gas region is here, okay. And the gas initially is not moving, but you move the boundary tangential to the gas region. Then what happened? Well, immediately, if you use the diffuse reflection boundary condition, then the boundary velocity of the gas will be half of this velocity of the shifting boundary. And then there's a layer, like a collision layer of with K. But as time increases, the jump of the velocity on the boundary decay at a rate t to the minus 1/2. And then the gas will move near the boundary, will move with the boundary of velocity v, and then gradually settle down at a far field to the original zero velocity Maxwellian. And this width of velocity region with velocity of the boundary or close to the boundary is t to the 1/2. And the transition from velocity close to the boundary to the boundary to the velocity 0 is the width is also t to the 1/2. Okay. Okay, so let me say that here is the initial data, which is gas not moving, but the boundary is a gas with velocity v in the y direction. And this is a positive C1 positive. And there's a diffuse boundary condition. So Son and Sensei did this in 1964. This is the first paper in the kinetic theory. Okay, I just mentioned this is Gore in his dissertation. He started analysis study, but for very, very short time. So, but what Sonny did, this problem is a very, very famous problem. So many people contributed. Cianciniani also contributed. Sonny Sensei focused on the phenomenon, this picture here. Significantly, this part here is a part where Hilbert expansion is valid. But in fact, here Sonny developed the Hilbert expansion in 1969 and 71 systematically. And he was motivated by this thing here. Before he used the Laplace transform to start this, and he just crank out, and it's not a theorem, okay, it's just an asymptotic expansion, but quite a conventional one. And so he then sees that after a while, it is a collision layer, and then the fluid-like wave. And so he then developed a Hilbert expansion there, where Hilbert expansion with boundary. However, up to this day, how do one study this whole picture? It is a evolution changing quite a lot of the wave type. And this is really the simplest problem for the coupling of initial and boundary layer. And yet we don't understand it. finally, let me just close by mention another problem that we also do not know. This just to indicate that this is a wide open field at the singular layers. So this is the multi-dimensional collision region. Okay. Let's look at the left picture here. So we have a smooth boundary, and with the gas inside this boundary. Now, if the collision number is very small, then one imagine that there's a collision layer near the boundary with the width K. And inside is a fluid-like region. And so one need to use the Hilbert expansion near the boundary to connect the collision layer to the fluid-like wave inside in order to start the whole wave pattern. And in this case, locally, actually, at any given point on the boundary, the collision layer one need to study is actually one-dimensional. Yeah, that's you have to go through here, but expansion. So it's a one-dimensional problem, just the one we talked about before. Now the curvature effect of the boundary come into the source term. Okay. However, suppose we have the bound even in this case, suppose the boundary data is not smooth. Say you have a boundary temperature has discontinuity, then still this picture is not right. The boundary layer, the collision layer problem would not be one-dimensional. Okay. And you know the radiometer, you shine a light, then this frame began to rotate. And this is the case where the boundary temperature is not continuous. And then another most severe situation would be that the boundary itself is not smooth. And in that case, away from the kink, this discontinuity of the boundary is one-dimensional, okay. And to study, to match the boundary to the fluid-like region, one need to only to study one-dimensional collision layer problem, like the one we talked about before. However, near the corner here, one need to study multi-dimensional collision zone. And this is largely open to analysis. I guess I'll stop here. Thank you.
Okay. Thank you, Tai-Ping.
Yeah.
So we don't have a real clapping. So I guess we have time for a few questions. I see Amit and Chiara turning on the camera.
Sorry, I have no questions. It was a lovely talk. I just wanted to show that he's not alone in the room.
Okay. Good. Other questions then? And don't forget to turn on camera and microphone at the same time. Yeah, Jeremy?
Oh, hi, can you hear me?
Yeah.
Okay, great. Yeah, thank you again for the talk. I just had a question if you could comment on some of the added difficulties if instead of a Boltzmann collision kernel that was the hard sphere model, like you wrote, psi minus psi star dot omega, if you change that to more general kernels. Still physically reasonable, but what happens when that's more singular?
Well, the exact answer is that I don't know. Okay, but I would say that none of these pictures that we draw should change. Okay, it should be valid, but of course they need a proof. Okay, they need a proof. I also mentioned, okay, because for example, perhaps let me say why Hart field is simpler. Okay, and this is in several places. For example, here, we look at along the characteristic, and this is nu, and nu is linear in Kc. Okay, this nu is linear in Kc, so it's really hyperbolic. If it's not linear in Kc, then the scale will not be so hyperbolic. Okay, and the green function, one would believe this should be true. However, if it is not Hart field, then there's analyticity for certain operator related to L. When you take Fourier transform, it will not be analytic. And so this is very sharp estimate is using company analysis. Okay, and that company analysis cannot be used. But one believes this should be true, but they will take a serious analytic effort. Yeah. Okay. So.
Thank you for the answer.
And to follow up, Tai-Ping, I imagine it would be really a mess technically, and I'm not even sure it's very interesting physically, but if you would put a non-cutoff long-range interaction for the L,
yes,
then I expect the fluid part would be the same, but you would have some sort of diffusive error around the particle-like part of the green function, no?
Yes. And this is this is a serious question. If one really want to go into it, yeah, that's a serious question. But perhaps this is suppose we say avoid this question for the moment, and then look at the picture. Now let me see which one I should look at. No, not this one. Okay, say if we look at this layer here, so in particular, you will be saying that this kinetic layer may not be a hyperbolic scale x over t.
Yeah.
Right? And it is not really hyperbolic. Right? And the viscous layer, as you say, perhaps is still okay. Yeah. Now this initial layer here, if it's non-cut off, then this become a little bit mysterious because solution immediately smooths out.
Yeah.
It's immediately smooths out. The race perhaps is okay. The race is perhaps okay, but the first one would be, yeah. Actually, I was studying this Boltzmann equation starting about the year 2000. And I was having a seminar with Tong Yan and Shi Xianyu. And at that time, I was proposing that how about non-cut off with Riemann data? Okay, because this will be a good signal problem to see how the non-cut off will have effect. Okay.
So you mean non-cutoff collision kernel together with the Riemann data?
With Riemann data.
I see.
Right. And this you really put yours. I forgot how to say it in English. You usually put yourself on the spot.
Yeah, and it is interesting physically, because I mean, I can imagine it's very hard technically, but the expectation would be that somehow the hypoellipticity slowly disappears in the small Knudsen number, and then the viscosity, the fluid viscosity takes over. There should be some sort of transition limit, right?
Right. Okay, yeah.
But yeah, quantifying that must be a total mess. But you think it would play a role on the boundary layer? So that
Yeah.
would be
Right. Okay. We had this discussion getting more and more intense. Now, I go back to what you said later on. Now that we're on this page, let me say one more thing. At that time, besides Riemann problem, I was proposing also the Green's function. Okay, that will be put yourself on the spot. Yeah, how that the non-cut off the Green function. So let's go back to the good old days, and this one. Okay, for the Haas sphere model. This, of course, as you know, this takes tremendous effort to get that far.
Yeah.
However, this one, this particle-like wave is very important for the analysis. And so let me just say indicate a little bit. Okay. Wait a minute. Where am I? I'm sorry, I'm kind of lost where the boundary. Okay, here. This kinetic wave with the delta function thing. This is something which I call a Gauss lemma. It says that this boundary integral operator, when you approach x equals 0 from the left and from the right, you obtain different things. Okay, from the left you get the b plus, from the right you get b minus, and therefore their difference is the whole b. Okay, I shouldn't say b plus b minus. They're different. Okay, the left and right, they're different. And why is that so? And this is because of this particle-like wave. So this particle-like wave is used crucially in this center stable, unstable decomposition in order to get this type of picture. And so to link this up with the center manifold theory, one needs this delta function. Now, I will imagine even though if the delta function is not so simple like this particle-like wave in the Green function, that the Gauss lemma still should hold. Okay, and so this is going back to your boundary layer and so on. You become a very subtle limit from the right and left. Yeah, it was very subtle limit. In our case, the limit is not so subtle because the delta function, you see it there.
Okay, much more. Yeah, even more complicated than I thought. Oh, you're
sorry. I should not give you wrong impression.
Okay.
Your camera has disappeared. Tai-Ping. No.
I see.
Okay, can I?
Yeah, and Claude, you can.
Okay, maybe I make it short because we have already.
Claude, start your video if you can.
Okay, start my video. Yeah, just comments. First, it was a super talk. Thanks. Second, going back to the prehistory, there was this paper of the shock profile of Nikolenko, Terber, Kaflich, Nikolenko. I have the feeling that what you get in this special case, first the question is, can you compare this problem with what you do? And I have the feeling that what it provides in this case, it's a much more precise description of what's happened when the Knudsen layer goes to zero for this problem. So I'm right or not, or can you comment?
You mean you're part of the Boltzmann shock layer, right?
Yeah.
Oh, okay. Yeah. You are right. Let me just simply say that we proved the positivity, but our profile is the same as the Nikolenko, Kaflich, and so on. And we use their profile, and then we do time asymptotic analysis. But at that time, we thought that the shock profile should be monotone, in the sense the pressure or the characteristic speed is a strict monotone along the shock. Because this will be convenient to use for the stability analysis, which we do to obtain positivity of shock profile. But we managed to squeeze through without using that. And this approach, as Claude mentioned, allow us to prove that the shock profile is monotone. Maybe
Yeah.
I just, okay.
No, that's a good, that's a super answer. Very good. Yeah.
Thank you. Claude, in your background, you have some Zen Buddhism, something there.
Yeah.
Yeah, you have some calligraphy about Zen Buddhism.
Okay, yeah. Yeah, I am moving from one camera to the other. Okay.
No, in your bookshelf, you have a...
Okay, here I am. Okay, last question is, or more crazy. What about comparing with the Kelvin-Helmholtz? You have
with what?
you look at the Euler equation,
Yeah.
with discontinuity, which propagate, which is called the Kelvin-Helmholtz.
Oh, I see. Kelvin-Helmholtz.
Okay. Then it should be approximated the same way, in some sense, by the Boltzmann equation. Maybe that's for future idea.
Well, for one thing, if something is difficult for order and never thought, then there are two possibilities. One, do the short time existence for Boltzmann equation, but that's not the real thing. The real thing is to really go to hook up with a fluid nonlinearity. But the fluid nonlinearity in the case you mentioned is terrible. Yeah, and so one perhaps can do something on the level of Boltzmann equation, but definitely you shed no light on the fluid nonlinearity, because that on the level of Boltzmann equation can only be harder and more complex, I would think.
Okay.
Yeah, but one can do a very short time thing, which is a very kinetic level thing, but that's not really in the problem. The ready problem, I mentioned that it takes a while to go to the fluid region, and that transition is a hard one.
Okay, great.
Thanks.
Okay, thank you, Tai-Ping. Thanks, Claude, also for the question. Maybe let's move on to the next talk. So let's just take a 2 minutes break for the time to have time for Maïr to.
Oh,